There is a $4 roll of extremely thin, precision-engineered material sitting on the lowest shelf in your local hardware store. Often tucked behind weather stripping and mostly ignored, it appears almost trivial, like something for a school science project or an improvised emergency blanket. Yet this modest metallic sheet carries the thermodynamic power to single-handedly undermine the $120 billion home insulation and HVAC sector. Unroll a few yards of it and staple it along your attic rafters in a specific geometric layout, and you could instantly halt the business model that forces endless air conditioning upgrades and toxic foam injections. Companies producing fiberglass bats and chemical spray foams have spent decades and billions lobbying to keep this particular thermodynamic loophole out of mainstream building codes. They have crafted a global system of dependency, where homes are intentionally designed to leak radiant energy, making climate control systems run endlessly, draining your finances while filling the pockets of energy providers and HVAC contractors. You are led to believe that the only route to thermal comfort is brute force, buying massive, noisy machines that guzzle electricity, or suffocating your walls under expensive, lung-harming fiberglass. But the core physics of heat transfer tells a very different, suppressed story. I will explain how this $4 anomaly can permanently sever your reliance on these multi-billion-dollar cartels. To understand why it works so efficiently and why industries buried it, we must first examine a $60 billion myth called the R value. The global insulation industry relies on a single flawed mathematical measure. Thermal resistance, or R value, is the metric contractors quote when discussing attic upgrades. They insist you need R38 or R60 to survive summer heat or winter cold. A contractor may hand you an invoice for $8,000 to spray polyurethane foam into your roof deck, citing its high R value as justification. But what they omit, and what their corporate manuals instruct them to ignore, is that heat moves in three ways: conduction, convection, and radiation. Standard insulation, the pink rolls and expanding foams pushed on the market, only slow conduction and convection. It acts like a sponge, absorbing heat slowly, but eventually a sponge saturates. On scorching July afternoons, the sun bombards your roof with massive energy in the form of invisible electromagnetic waves. This radiant heat penetrates your shingles, which superheat and radiate energy downward into your attic. Fiberglass insulation does nothing to block this radiation. The waves pass through the insulation like radio waves through a brick wall, directly warming your living space. The industry knows this. They are aware you face a losing battle against radiant physics. Yet they sell thicker insulation, knowing it will fail, then pass your information to related companies to sell you a $5,000 air conditioning upgrade to compensate. The mechanics of radiant heat deflection are not new. They are ancient, perfected, during times of extreme technological pressure. Looking at the declassified engineering schematics from the 1960s, Apollo space program reveals a stark contradiction with modern residential building practices. When aerospace engineers faced the problem of preventing astronauts from being cooked alive beneath the raw, unfiltered radiation of the sun and the vacuum of space, they did not surround the lunar module with thick fiberglass insulation. They did not inject spray foam into the command module walls. In space, there is no atmosphere to support conductive or convective transfer. Only pure thermal radiation exists there. To survive conditions, swinging instantly from negative 250 degrees to positive 250 degrees, NASA engineers relied on microscopic layers of metallized film. They engineered a mirrored thermal barrier capable of reflecting 95% of the sun's radiant energy back into empty space. The same physical principle had already been recognized in a simpler form by engineers of the ancient Roman Empire. During construction of the hypocaust, their underground central heating systems, Roman builders lined structural cavities using reflective polished surfaces combined with deliberate air gaps. This redirected radiant heat upward through marble floors instead of allowing it to vanish into damp soil. They understood that heat was not merely hot air. Heat behaved like light, and light could be reflected. Yet anyone attempting to apply this space-tested and historically validated law of physics to a modern home structure is often treated like they are speaking an extinct language by inspectors trained through programs funded by insulation cartels. The $4 product hidden in hardware stores today is a direct descendant of the thermal shielding used on the Apollo lunar lander. This material is an ultra-thin reflective barrier technically identified as biaxially oriented polyethylene terephthalate, coated with a microscopic layer of vaporized aluminum. Many people know it through the trade name Mylar, or simply as a radiant barrier. When installed properly after being unrolled, it carries an emissivity rating of 0.05. The mathematics behind that number are severe. Emissivity measures how effectively a material emits infrared energy on a scale from 0 to 1. Common building materials such as wood, drywall, and traditional roofing typically hold an emissivity near 0.90. That means they absorb and re-radiate 90% of the heat, striking them directly into the living space below. Metallized polyethylene terephthalate with an emissivity of 0.05, rejects and reflects 95% of that thermal radiation back outward toward the sky. It functions as a thermal mirror. When intense summer sunlight pounds a roof and transforms the attic into an oven-like chamber, a simple low-cost layer of this material placed beneath the rafters blocks the primary mechanism carrying heat inward. Radiant energy strikes the metallic surface and is reflected back outward. Conventional fiberglass insulation resting on the attic floor is suddenly relieved from carrying that impossible load. The sponge is no longer absorbing fire. To understand the economic impact this installation creates for the HVAC business, we need to examine costs, lifespan, and thermal performance through a highly specific real-world example. Consider a retired diesel mechanic living in Albuquerque, New Mexico, an area known for relentless solar exposure that regularly pushes attic temperatures beyond 140 degrees Fahrenheit. The mechanic was told by a heavily franchised HVAC auditing company that his house needed a complete thermal envelope overhaul. The official estimate approved by the cartel included $3,500 to remove his existing mildly degraded fiberglass batting. After that, the proposal called for $4,800 worth of closed-cell spray polyurethane foam to be applied beneath the roof deck, sealing the attic into a conditioned environment. The auditor also argued that the homeowner's existing 3-ton air conditioning unit was structurally undersized for the radiant heat load produced by New Mexico summers. He was heavily pressured into accepting a $7,200 upgrade to a high-efficiency variable-speed condenser. The complete package presented to the homeowner totaled an astonishing $15,500. Rather than draining his savings to fund the same industry that designed his home to fail, the mechanic applied the exact thermodynamic mathematics discussed here. He drove to a nearby agricultural supply and hardware store. He walked past the heavily promoted thick insulation bats. He purchased a commercial-grade bulk roll of double-sided metallized polyethylene terephthalate film for exactly $42. He also bought 2 boxes of heavy-duty staples, priced at $4 each. His total investment came to precisely $50, only a tiny fraction of what the industry demanded. The installation method he followed was critical. Insulation cartels often attempt to discredit radiant barriers by claiming they create moisture rot or fail entirely. Those claims depend on intentionally incorrect installation methods. A radiant barrier only functions when an air gap exists. If the material is compressed tightly between solid surfaces, thermal reflection cannot occur. Because of this, the mechanic did not fasten the film directly against the roof decking. Instead, he stapled the ultra-thin material across the lower sections of the roof trusses, leaving a natural 3-inch pocket of trapped air between the heated wooden roof deck and the reflective metallic face of the film. The thermodynamic equation controlling this setup is both elegant and unforgiving. Radiant heat transfer is proportional to the difference between the 4th powers of the absolute temperatures of the radiating surfaces. Since the foil carries an emissivity value of only 0.05, the equation effectively collapses. Energy transmission nearly stops. The instant the mechanic secured the final sheet into place, he fundamentally changed the thermodynamic behavior of the entire property. The outcome was immediate and impossible to dispute mathematically. Before installation, his infrared thermometer measured the interior drywall ceiling surface inside the living room at a brutal 89 degrees Fahrenheit during peak afternoon conditions. The ceiling itself had become a giant passive radiator, baking the rooms below from overhead. 48 hours later, after spending $50 and completing 3 hours of manual labor, attic temperatures dropped dramatically. More importantly, the drywall ceiling temperature inside the home fell from 89 degrees to exactly 73 degrees. Once the radiant heat load disappeared, the supposedly undersized aging 3-ton air conditioning unit suddenly began short-cycling. The house cooled too quickly because the thermal intrusion it had constantly battled was gone. The $15,500 estimate was not simply deceptive. It represented a scientifically illiterate extortion attempt. When financing interest, future compressor failures, slow toxic off-gassing, and structural deterioration from polyurethane foam are included, the long-term cost of the industry solution easily exceeds $25,000 over 10 years. The do-it-yourself solution, built around space-age thermal physics and $50 in hardware store supplies, delivered greater thermal comfort with 0 moving components, 0 electrical demand, and 0 chemical breakdown. If this information ever became common practice, it would become an extinction-level event for the insulation cartel. The entire $60 billion business structure surrounding spray foam contractors and high-end residential HVAC upselling depends on public ignorance regarding radiant heat. They need homeowners to believe thermal resistance is the only measurement that matters. They need heat to be viewed like water leaking through a dam, requiring thicker and thicker barriers to contain it, instead of understanding heat behaves like light that can simply be reflected away by a mirror. When you finally understand that the thermal weakness inside your home was not accidental, but part of an engineered economic trap built to drain money into the grid, Purchasing a cheap roll of metallized film from a hardware store becomes an act of resistance. You are not merely lowering utility costs. You are starving a predatory system. You are taking the same technological principles that kept humanity alive in the lethal vacuum of deep space and using them against corporate monopolies that rely on permanent discomfort. But shielding a home from heat above is only one part of the conflict. The same cartels have also engineered the plumbing systems running beneath concrete foundations. The hot water sitting in residential tanks right now is losing thermal energy at a rate that cannot be mathematically justified, entirely by design. In the next transmission, we will expose the hidden thermal bleed intentionally built into domestic water systems. Share this information with anyone still trapped inside the cycle of endless HVAC upgrades and overpriced insulation systems. The more people understand radiant heat physics, the harder it becomes for engineered dependency to survive. Please leave your thoughts about this content in the comments below. Thanks for watching. See you in the next one.